Okay, can you hear me? Okay, so I will actually spend a few words to introduce our speaker today, who actually then will give the this first colloquium in Italian, but I will spend a few words in English. So actually, it is a pleasure to have here Professor Eugenio Coccia, who actually will open this new series of colloquia of our department today. Eugenio Coccia is at present rettore at GSSI, di Gran Sasso Science Institute all'Aquila. He's a worldwide known experimentalist physicist in astroparticle physics, and in particular is very well known for his research activities in the field of gravitational waves. Professor Eugenio Coccia got his master's degree in Roma in the group of Amaldi and Pizzella. Then actually he was postdoc at CERN, at also Leiden University, at Frascati and the INFN laboratories at Gran Sasso. And among the different roles, scientific roles that he actually had, he led different experiments for the search of gravitational waves. In particular, now he's a member of the Virgo collaboration. And let me also mention that he was director of the INFN laboratories at Gran Sasso. He has been a president of the Italian Society for General Relativity and Physics of Gravitation, and also the president of the Scientific Commission, the International Committee for Gravitational Waves, for the gravitational waves. He got various prestigious prizes and honors. Just let me mention a few. In 2012, he got the medal Giuseppe Occhialini from the Institute of Physics from UK and from the Italian Society of Physics. And recently, in 2016, he actually also got the Special Breakthrough Prize for Fundamental Physics, together actually with his collaborators for actually, as we know, the discoveries of the gravitational waves. And so today, of course, he will tell us about how to explore our universe with gravitational waves. Thank you.
Thank you. Thank you for the invitation. Can you hear me? Okay. I will tell you something about exploring the universe with gravitational waves, and it's a pleasure to do that in the Aula Rostagni here in Padua. I see here many friends and colleagues. I am happy to see them. Let me say I will try not to be so specialized, especially not at the beginning, so that to have quite a wide audience following what I would say. And I will introduce a little bit of history, of course, and it's starting with how before Einstein we saw gravitation. And as you know, this famous drawing of Newton himself is that if you go on the top of a mountain, if you throw a stone, the stone falls here. Then if you throw it with a larger speed, it falls a little more far, and still a larger speed, it falls here. But if you throw with a large speed, large enough, it will continue to fall without impacting anymore on the Earth. And so it will go around the Earth in orbit, I would say. So his vision is that the moon is falling on the Earth. The fact that it's suspended there gives us an impression and is a poetic view, but actually the moon is falling on the Earth. Of course, does not impact the Earth because its orbit is larger than the dimension of the Earth. So the Earth is falling on the Sun. And in this picture, is quantitative because there is a force attracting any two masses with this equation, which is very, very famous. And this view, the fact that space is absolute, time is absolute, and to explain what happens, you have to introduce a force there, a force of attraction. This explains everything. I mean, this explains a lot what is in the universe, since the only other long-range force, the electromagnetic, has two charges, plus and minus, which tends to have a neutral result. Actually, the force which is sculpting the universe is gravity, which is adding. It is impossible to neutralize the gravitational charge. So at the end, there is gravitation which gives shapes to the universe. Shapes means stars, galaxies, and the was as we see it. So Newtonian mechanics was so successful that there were no reason in principle to change. Squadra che vince non si cambia, we say in Italian. So why we needed Einstein then? And why what Einstein said? Well, the vision of Einstein started with the happiest thought of his life. This is what he said. And the happiest thought was if a man falls from the roof of his house, for instance. This is actually happened really where he lived. He was in Zurich at that time. So if a man falls, while he is falling, everything falls with him. If he has something in his pocket, for instance, a coin, the coin falls exactly like everything were without any force. It doesn't feel any more gravity during the free fall state. So this was the happiest thought of his life. It's very simple. But this was the beginning of a series of other thoughts elaborating on that, and in which actually he compared the state of free fall to the state of being far in the universe, far from any gravity source. You are free there exactly as you are free falling in a gravitational field. And if you are in a gravitational field like we on the Earth, so we feel that we have a weight and all the other things falls with the same acceleration, this state is equivalent of staying in space but driven with a thruster at exactly the acceleration of g. This state is equivalent to the gravitational field. So this, which is known as the equivalence principle, give him thoughts about these things, that if you have a light ray, for instance, you are in zero motion, of course, it goes straight. It is by definition, by definition, the geodetic is a straight line, is the line with minimum distance between 2 points. And light follows this path. If you have a constant velocity, then of course you see this like that because you are moving in mean time. But if you are accelerating, then the ray of light bends. There is a curvature. So the fact that gravity induces a curvature in space or in space-time, this was where he started to his elaboration of the general theory of relativity. In the talks for the general public, So this is a very, very simple view. I always repeat this drawing to explain the view a la Newton respect to the view a la Einstein. And the view a la Newton is the following. If you suppose two small physicists thinking to live in a flat space, completely flat, a table, like the Earth, people which thinks that the Earth is flat, it's completely flat. And in this flat table, if they start moving with the same speed in a direction perpendicular to the direction of the other, you see that they will follow parallel line, so the distance between them will not change. This is what they think. Actually, they do that, and they see that they go near and near. How to explain that behavior? So they, which do not discuss the geometry. The geometry is flat. It's a Euclidean geometry which holds. So the consequence is that they at the end could conclude, a la Newton, that there is a force attracting them. This is a possible explanation. When we go in this direction, there is a force which attracts us. This is a possible conclusion. So the view a la Einstein is different, and is that maybe the geometry is not flat. Space-time is not a flat table. Maybe they live in a curved space, so like the surface of a sphere, for instance. Then, if they start, for instance, here, the equatorial line, they go straight, going in a direction perpendicular to the line joining with the other, they will reduce the distance, not because there is a force attracting them, but just as a consequence of the geometry they live. So this is the heart, if you want, of general relativity. There is no gravitational force. There is not a force. It's simply the geometry which is not flat. And if you think the geometry is not flat, then you doesn't need anymore this ingredient of a force. Of course, the curvature is given to something, is given to the mass and energy deforms space-time. But once they deforms the space-time, then everything moves free, following the geodetic lines of that curved space. So the Earth goes around the Sun because this orbit, this trajectory, is the geodetic line in the space-time deformed by the presence of the Sun. All that, of course, has an equation which is not easy to explain in detail, and I will not do that. It is simply, here it is a tensor, it is the geometry, it expresses the geometry of the space-time, and if this is a certain tensor, the flat tensor, let's say, then this means that the situation is the simplest possible, Euclidean geometry holds, you are far from masses and energy. But if this is not zero, so if this is the mass energy tensor here, then you will have a geometry which is not completely flat. And this is a coefficient which is full of interesting constant, like Newton constant and speed of light. The most important and the most surprising symbol in this equation is this equal. The fact that the geometry is equal, a part of that coefficient, to the distribution of mass and energy in space-time. This is why it is marvelous, this equation. So, given in, as I said, this is a slide for a general public, so it's very simple, but for Newton, if there is a mass, the space is absolute, time is absolute, nothing changes, nothing in the geometry or in the flow of time, they remain the same, even in presence of a mass. Following Einstein, this is not true. The visualization is in 2 dimensions because you can visualize easily in 2 dimensions. But in the reality, the mathematics allow us to put this form in 3 dimensions, 4 dimensions, what we want. So the following Einstein, the presence of the sun deforms space-time around, and so everything moves, like said John Archibald Wheeler, space-time tells matter how to move, matter tells space-time how to curve. And this is the simple content of the general theory of relativity. To make things even simpler, let's say, to visualize what is a space-time deformation, it is easy to deform space-time, or is it difficult? Then consider a very simple equation, the equation of a spring and of a force deforming the spring. So here, the geometry is the displacement here. The force is the reason why the geometry changes. And K here is a lasting constant, is the proportion between these two factors. Well, to physical things. Then this is, can be compared with that. Here the geometry, here is the force, let's say the reason why the geometry changes, and this is a coefficient. So force play the role of the energy tensor, mass energy tensor, the displacement play the role of the geometry, and this constant means, this lasting constant tell us how stiff is the spring, then how stiff is the space-time is given by this constant here. And this is a very, very large number, because C is already large, at fourth power, G is small, so the stiffness, the elastic constant of space-time is enormous, 10 to the 45 kilogram per square second. This means it's very difficult to deform space-time. Space-time is, if you want to see it as a matter, is the stiffest things in the universe. So you need the sun to have a physically observable effect, if you want. A large, macroscopic, astronomical mass. And this is the experiment which gave to Einstein the notoriety that he has since then. He became an iconic person after this experiment. This is the experiment of the deflection of light during an eclipse. If it is the position of the star, because of the deformation of space-time due to the sun, the trajectory is curved, so when it arrives to the Earth, actually the apparent position of the star is different from this one. Of course, you need to have the sun here, so you need to have the moon in between to obscure the sky behind the sun. And this is what Eddington, with the famous travel in the Prince Island, there were two missions actually, but this was the famous one, in which the stars which were behind the sun actually changed their position. And this was reported on every journal in the world and giving to Einstein the notoriety that he has since then. Not only space is deformed, also time is deformed because of gravity, because of the deformation of space and time. And this was another very famous experiment, the redshift experiment by Pound and Rebka, which was actually in an elevator tower in Harvard. And it can simply be stated that if you have a photon, the photon going up, this is a large gravitational mass, and going up, it gets red. There is a shift in the wavelength. Well, everything goes up, lose energy. This cannot lose velocity because it must go to the speed of light, but still can change something, which is the wavelength. And actually, this redshift was exactly measured. Now, one consequence of this experiment is fantastic, and it allows to travel in the future. Ta-ta! I attract your attention now. So why? Because you can think this is a clock. A clock here, and the crest here, the top of the wave is a tick of your clock. So your time here is tick, 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 tick. You can think of a mirror there, and so the light goes back and forth, and you have tick, 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 tick. You have your watch. So you want to communicate to another person here, where gravitation is lower, how fast go your time. So you send to him this tick, 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 you send. And if you send up, since there is a shift in the wavelength, he receives tick, tick, tick. So he thinks things there are going much slowly than here. The same clock here, of course, the same clock put here, give tick, 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 like this one. But if you send a signal from here to there, the signal can even be a camera viewing on the top on a window in which he simply does like that. So the other will see, and he can think, oh, why it goes so slow? Because the time is changing its speed. So 1 second here may become 1 year there. So it depends on the difference of gravity. Time does not flow at the same rate. And this is very famous. I mean, a watch here and a watch there are not saying the same time. This goes slowly, this goes faster. And this is one of the effects that we say it is possible to travel in the future. Because if you go near to a strong gravitational field, your time is slower than people which remained at home. So 1 month for you there is several years here. And then when you come back, you find that for you is passed, I don't know, 1 year, and for the other passed 100 years. You will travel in the future, in a sense. And this are full of science fiction and films, but this is not science fiction, this is science. Traveling in the past is impossible, traveling in the future is possible in this way. Naturally, this deformation, space-time deformation can be very large because we saw the sun, already the sun deforms space-time enough to have the planets around going in rounds, in ellipses. If you have a compact star, so mass much more concentrated, so gravity is stronger, let's say, for in Newtonian words, gravity is stronger, then this means that this deformation is more pronounced. And for a neutron star, which is even more compact, is even more pronounced. And there is a limit in which the mass enters inside the sphere, which defines the limit in which not even the light can go out because the gravity is too strong. This is the event horizon. And in general relativity, this is a limit of no-return, say. So you can go even near. If you have a motor strong enough, you can escape. But if you pass the event horizon, you cannot escape. And the general relativity equation says you go with no possibility of stopping through the singularity, which is this is the vision, I mean, the consequence of the general relativity of Einstein. Actually, this condition of compact object, compact stars, black hole, is a condition that we find in the sky. The evolution of stars starting from a hydrogen gas up to the state of a real star, and then of an explosion which which imply an implosion, and so a very compact object, which can be a white dwarf, a neutron star, and a black hole. These are objects, compact objects we have seen in the sky. We see in the sky. Actually, for what regards the black hole, which is the most mysterious one, the equation of general relativity say that this is not a mass, really. There is empty space inside here, and all the mass is at the center. This is the extreme position of the general relativity equation. What enters does not remain there, just near to the surface. It goes inevitably at the center in one point. It's like if matter reveals its intimate nature, which is to be a concentrated of space-time. I said it's like if because this is not known, actually, if here there is really a point in which there is all the mass or there is something else. But however, what we know, not only from the equation, but also from astronomical observation, including gravitational waves signals, is that these are regions of space created by superdense matter from where nothing can escape due to the strength of gravity. In other words, the escape velocity is larger than the velocity of light just inside this surface, so nothing can escape. Some may form when very large stars collapse and die, expected to have masses from around 3 to hundreds of times the mass of the Sun. This is true for black holes coming as a consequence of a stellar evolution. Stellar evolution means that the star is strong enough at the beginning to collapse to black hole. This means 5 to 10 solar masses minimum. And actually we found with gravitational waves masses larger, 60, 100 solar masses. So they exist, very big black hole. It's not clear how they are generated. They may be generated even in the Big Bang itself before elementary particles forms. Just at the beginning of the Big Bang, when there is energy which can have let's say density fluctuation in such a way that some energy feels itself in a space so small that it forms a black hole. This primordial black hole is a subject very, very interesting, which have been revitalized recently. And then there are also supermassive black holes at the center of the galaxies. Also there is not clear how they form, how they have been developed by accreting matter. So there is a soap bubble, black, is a fantastic object. And why I show this? This is not publicity. This is how the universe is following Einstein to introduce the subject, the issue of gravitational waves. Actually, following Einstein, the universe, the space-time is flexible. It's flexible. It's something in which the presence of energy and mass deforms, and if something like two stars moves one around the other, they must generate a wave. They lose energy because they generate this wave, and this wave is a perturbation of what? You know, with electric field and magnetic field, you know, electromagnetic wave, what is the physical entity which vibrate, which change. What is the perturbation here? Is space-time. The space is perturbed in a wave traveling at the speed of light. And this was a consequence of the general relativity equation. In the weak field approximation, in which the metric tensor is the one of flat space-time plus a small perturbation. So if you put this in the 10 nonlinear equation of Einstein, you can solve the equation. I mean, the Einstein equation becomes the D'Alembert equation, is a magic. So for this perturbation travels with the speed of light in vacuum, and this is a solution of this equation, which is an approximation valid with this with this position respect to the Einstein equation. And those are gravitational waves. Space-time perturbation propagating in vacuum-like waves at the speed of light. They have some distinctive features which are a consequence of the equations, of course, of general relativity. They have two transversal polarization states. This is like the electromagnetic case, but now they are peculiar, you see? There is something like a tidal. It is a tidal movement that it's propagating. And the other polarization states is, if you want, the same pattern tilted of 45 degrees. They are associated with massless spin-2 particles, called gravitons, and they are emitted by time-varying quadrupole mass moment, no dipole radiation, and this is a very big difference, of course, with respect to the electromagnetic case, because of conservation laws. In fact, if you try to expand in multiple the energy lost by a gravitational system, you see that the dipole term must be zero, because this is for the conservation of the linear momentum. And so the first non-null term is the quadrupole one, which is, of course, has a suppression factor of this kind. So the gravitational wave, the amplitude of this perturbation depends on the second time derivative of the quadrupole component. So to compare electromagnetic waves and gravitational waves, you see that this is the case of electromagnetic waves, the two polarization states, and these are the two polarization states of the gravitational wave. I like this statement of Lord Kelvin, because Lord Kelvin is someone near to us. I mean, maybe a little more than 100 years, let's say. And they say that so-called electromagnetic theory of light has not helped us hitherto. It seems to me that it's rather a backward step. The one thing about it that seems intelligible to me, I don't think is admissible, that there should be an electric displacement perpendicular to the light of propagation, which is natural for us. We know the electromagnetic field is acting perpendicularly to the line of propagation. What seems trivial for us today was not at all for giants of physics. So this is how science works. I mean, if you have difficulties, if you want today, we have not to be so severe with ourselves. So if you have a system of masses in a circular arrangement, for instance, why does it work here? Okay. This is how a circular arrangement of masses will move when a gravitational wave passes. This is one of the two polarization states. So if you want if you have a test student and there is a gravitational wave investing him, so this is what you can expect. Unfortunately, the effect is much, much smaller. It cannot be visible with your eyes. And how much smaller it is extremely small. So small that when Einstein himself calculated, the amplitude of the gravitational wave in cases which he could think, at that time, is that in any case, one can think of A, the amplitude, will have a practically vanishing value. So he thought of big cylinder put in rotation at the limit of the breaking limit, and the amount of gravitation, the amplitude of the wave is so small that you can forget it. And this was the position we dominated for many, many years. How small is Well, at the time of Einstein, he didn't know about neutron stars. Black holes was something like exotic and a dream. But the fact that the universe is so violent was not in the menu of the physicists at that time. Now we know that actually supernova explosions, even more neutron stars merging, or black hole merging, the signals that we have seen, actually have gravitational wave amplitude of the order of, which are the practically value we can think of, is something like 10 to the minus 18. 10 to the minus 18 what? Meter? No, it's a deformation. It's delta L over L. It's relative displacement, so it has no dimension. This means that 1 meter, if you think of 10 to the minus 18, this means that 2 points in space at 1 meter distance, they change this distance of the order of 1/1000th of a billionth of meter. 10 to the minus 18 meter on 1 meter. And how small is 10 to the minus 18 is, for instance, it's interesting to say that the human hair has only 0.1 millimeter thickness. It's small. The atomic diameter is 10 to minus 10 meters. The nuclear diameter is 10 to minus 15 meters. So you see, you are thinking, you are trying to detect something smaller, displacement smaller than the diameter of a nucleus. So you have to divide by 1,000 the nuclear diameter to get 10 to the minus 18 meter. And this explains why 50 years of experimental efforts were needed to detect gravitational waves. It was not easy at all. So there is no laboratory equivalent of Earth experiments for production of gravitational waves. This is what we know. This is why it is difficult to produce, and we have to rely on astronomical sources. The luminosity, short calculation, due to a certain mass and size oscillating at a certain frequency, you can see that it depends on the quadrupole moment. So having the simplest expression for the quadrupole, you can see in the Einstein case, the example of Einstein, 1,000 tons steel rotor, frequency of 4 Hz, then the luminosity is 10 to the minus 30 watt. And then the practical evaluation value. But we know now that, for instance, there are in the sky neutron stars, 1.4 solar masses, and the luminosity in this case is 10 to the minus 52 watt. So what was a practical evaluation value became, for the experimentalist of the last century, a challenge for contemporary experimental physics. And the objective, why it is important, what was important to detect the gravitational wave, there were 3 main answers. One is that this is a prediction of the general relativity of the relativity, and so we have to see if this prediction is correct, if general relativity holds also for its dynamic feature and behavior. The other was because, of course, there is alternative theory of respect to Einstein predicting a behavior, something different. Then it is important for astronomy, astrophysics, to look beyond the visible, to look to dark region in the sky, to understand black holes, neutron stars, supernova, understand gamma ray bursts, for instance. And then there is a cosmology reason, which is twofold. One is that there are sources which are standard candle for gravitational wave emission, and so you can know how you can determine the Hubble constant with having signals of gravitational waves. But the other reason, and maybe is even more important, it's that the graviton decoupled from the primordial plasma much before neutrinos, much before the photons. The photons decoupled when the universe was already 380,000 years old. So it is an image, the cosmic background, of the universe very young, but already with 300,000 years behind. The neutrino decoupled after 1 minute, I think, from the Big Bang. The gravitons decoupled 10 to the minus 30 seconds, something like that. So it is the most pristine, primitive signal coming from the universe. And about sources and physics that we can do, we have many types of sources with the time scales of the signal much different. The supernova happens in a time scale of milliseconds, for instance, and you can get information on the inner detail dynamics. You can see neutron star black hole being formed, and you can have information on nuclear physics at high density. So this is a signal, supernova, we have not yet seen in gravitational waves, but it will be very important. This is another signal we have not seen directly, at least in gravitational waves, which is the spinning neutron stars, the pulsars, rapidly spinning neutron stars. If they have a shape which is not perfectly axisymmetric, there should be a mountain somewhere, let's say, then rotating, they have a quadrupole moment, as they can generate gravitational waves, and there is of course a modulation depending on the relative movement of the source with respect to the detector. And information here is also very important. You can see neutron star location, neutron star physics, and pulsar evolution. This is the signal which we have detected, the class of signals we have detected, coalescing binaries. Two compact objects spiraling together from a binary orbit. They, of course, lose energy because of the emission of gravitational waves, so they go near and near. As they go near, they increase the speed to conserve the angular momentum. So it is something which at the end it terminates with a signal increasing in amplitude and in frequency, a signal shape increasing in amplitude and frequency, and this is the shape we have actually detected many times now, at least 20 signals of this kind. And the information here is that you can get the masses of the object from the shape of the signal. You can identify black holes, so you can see the distance of the system, and you can so determine the Hubble constant comparing with the redshift of the source. And this is a test of strong field generativity, of course. Then there is the signal background, which I told before, the echo of the Big Bang in gravitational waves, not in photons. So, and here you need at least two detectors and have to detect a coherent driving force in these two detectors to get this kind of background. Is it may be the most important, but also the most difficult. We are still far from this part. So, for instance, if a neutron star falls in a big black hole, this is the shape of the waves. There were many contributions in time to various people since the beginning of the story, but there is 1 year which is important in the story of gravitational detection, with this 1957 in the Chapel Hill meeting. At that time, there was no discussion of black holes and neutron stars because the object was still barely imagined. But attention was devoted to the physical reality of gravitational waves, and in particular focused on the question of whether gravitational waves could be understood to interact in a physically meaningful way with the detection device, or if a gravitational wave simply can be put to zero with the changement of coordinates. So is a physical effect or is not a physical effect? At that time, the debate was very vivid, and Einstein was not already with us at the time. I think he died in 1954, but before he dies, he had many doubts, Einstein, about the existence, about the possibility to measure gravitational waves, not because of the smallness of the effect, but in principle could not be measured, because he It is all an artifact of the coordinate system. And at that conference, in particular, Felix Pirani made a very clear point, a clear transparent connection between equation of geodesic deviation and Newton's second law. So identifying the Riemann, some Riemann component with the tidal field. And so at that conference there were many, many important physicists present, like Feynman, Bondi, Wheeler, and at the end, the conclusion of this conference was, yes, gravitational waves exist, they can be detected in principle, they can be detected. And Joe Weber, this man, was present at this conference, and so he started trying to detect with very simple instruments at the time. They were something like a diapason, let's say, so some like oscillators. When gravitational waves arrives, these things should be put in movement. It excites the fundamental longitudinal mode. And you have here piezoelectric ceramic glued on the surface of the cylinder, transforming, converting the mechanical strain into an electrical signal. Very, very simple, very simple. Too much simple, maybe. In fact, was much more difficult than that. In the meantime, in 1974, there was this indirect evidence which, if you want, gave a boost in the field. People were confident they exist. And this is because of the discovery of this binary pulsar, 1913 plus 16, and for which these two guys get the Nobel Prize. So it is a system which loses energy. Actually, it is possible to monitor this because of the fact that one is a pulsar, so you can a clock which is very, very precise, and the energy lost can be compared with the prediction of Einstein as energy lost in gravitational waves. So you see here that this is their experimental point. This is not the best fit. It is the prediction general relativity, you see? And this was absolutely fantastic to see that a real system in the sky, a real laboratory that you cannot replicate on Earth, of course, a real laboratory there were behaving in such a way that Einstein was right. I mean, gravitational waves should exist. The system loses energy as Einstein predicted for gravitational waves. The acoustic part detectors groups were around the world. Here in Italy, the group of Edoardo Amaldi, this is myself many years ago, and the group of Massimo Cerdonio, which is here, and which is, I am happy to see Luca Taffarello here in the audience. We spend a lot of time cooling down this object to reduce thermal noise, employing superconducting devices to convert a mechanical signal into electric one, but we were not succeeding, actually. So there was another kind of detector, the successful one. All the field of bar detectors actually reversed in this new technology, in this new field, and this was the right one. So the LIGO and Virgo interferometers were the successful instruments. You have here the three fathers of LIGO for different contribution. Actually, Ron Driver is missing here. And here the two fathers of Virgo, and let me especially remember our friends Adalberto Giazzotto, without which Virgo will be not there, but probably LIGO will not be successful yet. So, and how cannot avoid to explain how it's possible to measure a billionth of a meter displacement in a very simple way, but let me show you this. The principle of this instrument is a Michelson interferometers. So, you know, the Michelson interferometer is the one of the constant speed of light, not depending on the frame of reference. So, it's a fantastic experiment. So, this is the evolution of the Michelson interferometer. This is it is a laser. I mean, in this conceptual drawing, this is the laser. This is the beam splitter. So the light from the laser is divided in two. One part is transmitted, one part is reflected to these end mirrors, which then reflect the beam, and they send the beam to a transduce to a detector, light detector. So in practice, let me animate this thing. No, let me animate this way. Very simple. Let me say, the light from the laser divides in two, you see, the beam. It goes to the end mirror, is 3 kilometers, 3 for LIGO, for Virgo. And then you see, when they recombine, how they recombine? If they recombine in opposite phase, then there is dark here, no wave, this is virtual. But if a gravitational wave arrives and the two paths change one relative to the other, because gravitational wave has this tidal effect, you see, then you have here a spot of light changing with the frequency of the gravitational waves, and the intensity gives you the amplitude of the gravitational wave. This is the successful instrument, which is not so simple as I show you. There are a lot of noise sources, of course. At low frequency, there is the seismic noise, the suspension thermal noise, the shot noise at high temperature. It is a fight against the noises. So the real detector is all under vacuum and employing high-power lasers and many tricks to increase the sensitivity. But I don't want to be long on that because all the practical details are in the publications. Just let me remind you that the effort of detecting gravitational waves is the effort to arrive to a certain sensitivity curve. This is the gravitational wave amplitude you can detect. This is frequency. And you have that the sensitivity of the detector is depending on seismic isolation, on the quality of masses and suspension, on the high-power laser. So there were many years spent. You cannot buy this on a catalog. You have to develop yourself in the laboratory. So this means many, many years of hard work, of course. But then, at the end, today, we have 3 detectors of the advanced class, as we say, 2 LIGO in the US and Virgo in Italy. The 2 LIGO were funded 2 years before LIGO, and they actually have the privilege of detecting the first signal. And this is the first signal. This is the noise of the interferometer. You can imagine the spot of light in the detector, which fluctuate a little bit because of the various noises in the detector. But you see at a certain moment, this fluctuation takes a shape of a real wave. Very interesting. The other detector, this is one in Hanford, the other in Livingston, Louisiana, has a similar behavior. Actually, if you subtract the noise, you have the same shape of the wave arriving there, which can be seen also in a frequency time domain. This is how in time the frequency goes up, you see? And actually the sound of that is, you may have heard this various times. This is the acoustic frequency range. So if you put the signal into a loudspeaker, you have something like that. It's a chirp, in fact, the name, because it sounds like the bird voice. And for black holes is a little slower. I mean, oh, something like that. This is how this system behaves in the sky. And the shape of the wave tells us that there are 2 spiral black holes, 36 solar masses one, 29 solar masses the other. So, and this is the last phase before the merger. At the moment of the merger, the velocity, the relative velocity was more than half the speed of light. You can imagine 36 solar masses, 29 solar masses impacting at the velocity that we are normally taught for cosmic rays or particle in an accelerators. And this was was a camera on that point of the universe would have taken. This is slower to appreciate this dance of the two black holes. You see the reconstruction here, it takes into account the Einstein lensing effect all around. The light which are behind are seen in multiple view. So at the end, the two black holes penetrate one inside the other. No light goes out. It's a purely gravitational signal. Only a space-time perturbation traveling the speed of light goes out. So it is better to see it here. See, the crest of the wave is the maximum of the amplitude. It is at the end that you have the top of the amplitude of the wave. This traveled for 1,300,000,000 years in the universe before arriving on the Earth on September 14, 2015. The waves passed through the Earth. This is very exaggerated, of course, this effect. But this is to show that also the Earth reacted to the passage of gravitational waves. But this time, there were detectors with the sensitivity able to succeed and to see the passage of this wave. Well, I am in the final part of my conference. However, let me say, this is the paper on physical wave letter with the shape of the wave. The server of physical wave letters crashed the day for the first time because of the number of downloads for this paper. There was a Nobel Prize for Barry Barish, Kip Thorne, and Ray Weiss. And after that event, we saw several other black holes, several other systems which are here. We are represented. For everyone is GV, the name, and then year, month, and day. And these are the last fraction of a second of the wave. The waves are different. You see, there is the signal. The first signal was actually a large amplitude wave, but then we detected a signal with an amplitude which is much lower. And it is important to understand what is the method with which we detected even very tiny signal if they last for enough time in the bandwidth of the detector. And this is the matched filtering, let's say, method in which you have noise. Hidden in the noise, you have a real signal, but you don't see if there is a signal. You don't see with raw data. So you need to pass what we call a filter, which is a certain waveform prepared to be similar to the expected signal. You have a bank of templates with all possible value of masses, of spins, and you pass the filter with your prepared wave, and if this wave matches the signal, then you see the signal, even if you were not possible to see the signal before. Of course, you want to pass many thousands, millions of templates on the same data. For instance, this is the case of the gravitational wave taken in 26th of December 2015. You see the raw data are this one, the blue, the red one. Hidden, there is a signal, but to see this signal, you need to pass this matched filter. So we tested the general relativity. There is no dispersion term, so the signal we detected has not lost its feature, its form, its shape respect to the signal emitted. perfectly fits with that masses of black holes and that features. So this means this put a limit on the graviton mass. If the graviton have a mass, then not all the frequency go to at the same speed. You have a dispersion in the waveform. So we have now a limit of graviton mass, which is, I think, better than the limit on photon mass. Also, there is a lot of new astrophysics, because we had before knowledge of small black holes due to X-ray studies, to accretion disk around something which maybe was a black hole. Now we have a class of much larger black hole, you see. We know stellar binary black holes exist. They form in binary pairs. Was not obvious, because they merge within the lifetime of the universe, and the masses are much larger than what was known about stellar massive black holes. These are already the first surprises of this kind of new astronomy. But it is not only black holes. We detected also a binary neutron, at least one case, more than one, but one was spectacular on August 17. Let me conclude with that, because this is the beginning not only of gravitational astronomy, but also multi-messenger astronomy. That means studying the universe with multiple messengers. Up to now, only photons. Now we have photons and gravitational waves. And of course, neutrinos. We have just already some neutrino features all around, but what was spectacular was to understand the power of the gravitational wave alarm. It has been said that gravitational waves is like the sound of the universe. It's like some kind of music. It's a vibration of space. It's not vibration of the air, which is the sound here on the Earth, but it's vibration of space. So can be compared to the sound wave. So if you are in a place and you hear a noise, you don't see nothing, you hear a noise, but you know there is something happening there, and so you go in this direction with the eyes and you see what happens. This is typical every day. We hear and we see. Now, with the gravitational detector running, we have the possibility to point, to say something is happening there, in that region of the universe. Something which means two black holes, two neutron stars are merging there. So we can tell to the astronomers which have the traditional telescopes, traditional and modern, of course, telescope, I mean gamma ray telescopes, optical telescopes, radio wave, X-ray, all kind of traditional photons detectors to point all together immediately with seconds of delay in that part of the sky where we hear some noise. And this is, for instance, what adding Virgo had in one topical case. You see, with only the two LIGO, you don't know very well which is the region of the sky where something happened. Adding a third detector like Virgo, you have a more restricted region. So you can confidently say to the astronomers, look there, and they have to restrict restrict attention, of course, as much they have the probability to see even a faint signal. So this person which was here in Padua, I understand, a few days ago, Marica Branchesi, is what coordinated the gravitational wave detector alarms with the astronomical telescopes. And in fact, on 17 of August 2017, while the gravitational wave detector had this signal, at the same time, the Fermi gamma ray detector, after 1 second, they had a gamma ray burst. So the gravitational wave detectors said to 70 telescopes on the Earth to point in a certain region of the sky. Life is hard. Okay. And what I show now you is something which is really moving for me, because we said to look in this region to the telescopes, and they go to see what happened there for in the minutes after the alarm, and they saw in a place which was which passed absolutely unperceived, if not for the alarm. They saw in a galaxy which was very not important at all, this point, this spot, you see? This is the Relativity Survey telescope in Chile. And this changed in the minutes, hours, days after. You are looking online on two neutron stars merging. This is fantastic. What happens just in the time after the merging? Two big nucleus that compenetrate one respect to the other. And this is the brightness. You see here the time after 2 days, 2.3 days, 2.4 days. You see the light coming from that part from that region, how it goes down. And all these peaks, you see, they are telling us which are the chemical elements forming in that moment in that part of the universe. And this was absolutely fantastic to see that there were lines referring to the heavy elements in the universe. So we know that formed by merging neutron stars are all these elements, many exclusively, say, in this kind of event. So the reconstruction now is clear because of the gamma ray, gravitational wave, and all the telescope observing. It had the two neutron stars in that part of the universe. They collapsed, they merged. There was a gamma ray burst, and then in hours and days after, all this heavy matter forming in this part. And of course, heavy matter and nucleus, which are constructing other planetary systems, maybe also. As a matter of fact, it has been calculated, this is what impressed the general public much, that there was formed gold in an amount of 100 Earth, 100 times the mass of the Earth in gold there. It's something fantastic because you see, we know that the Big Bang, from the Big Bang emerged very simple ingredients, hydrogen and helium basically. The present universe has many other elements in various percentage. We knew that stars are making many elements up to iron. Then there were heavier elements than iron, which were not clear, which was the source of that. Supernova could be one, certainly, but supernova, it was not convincing for the really heavy elements. So there was this sort of mystery. So we know that, of course, there are stars which have the birth phase, the developing phase like our sun, and then in the case of explosion of stars, after the core collapse, the elements formed are spread around. We know that, all this information are a sort of mirror towards us. We are made by, in this percentage, by oxygen and carbon, nitrogen, calcium, phosphorus, potassium, sulfur, sodium, and many others, including heavy elements. So we are studying what was the source of others possible Earth, and this is particularly fascinating. This is the book of Galileo, in which he started the modern astronomy with the moons of Jupiter, and this is the paper. And for all the new astronomies, the first sources were surprises not predicted before, like the Jupiter's moon, like the muon in the cosmic rays. Who ordered the muons, said the rabbi. In radio waves, we have learned of giant radiases, of cosmic wave background, of pulsars, of X-ray banners. I mean, of course, gamma ray bursts were not predicted at all. Now, with the gravitational wave window, we know that there are massive black hole mergers. And a question which is also fascinating is all these black holes maybe are too many. We're not expecting such a large number of black holes, such massive. Can they be the solution of the dark matter problem? Probably not. But, however, it is a question which is interesting to raise. Well, I want to be to the end because, of course, we have interesting perspective. All the field, the gravitational waves, took a boost from this detection. So we are thinking on new interferometers on the Earth, a new generation, underground to reduce seismic noise, cooled to low temperature to reduce the thermal noise, so to pass from this sensitivity curve to another, one order of magnitude better, which means an order of magnitude of space of the universe, which can be investigated 3 times in volume, 10 to the 3 times in volume, 1,000 times in volume. And this is another project which is in the space. To put an interferometer in space will, of course, get rid of any terrestrial noise, and this can be sensitive to another range of frequency, which is this one of the millihertz. So the large interferometers on the Earth will continue to investigate the compact binary coalescence, neutron stars, black holes, pulsars. The LISA can investigate lower frequency source, like supermassive black holes, coalescence, for instance, and as also binary far from coalescence. We can see, for instance, a binary system signal, gravitational wave, passing in the LISA bandwidth, and then after hours or days, passing in the bandwidth of LISA. It is a very peculiar alarm, it will be. Then, at lower frequency, we have pulsar timing of radio telescopes, which try to detect fluctuations in the possibility of gravitational waves in the clocks, which are the pulsars. And the cosmic background polarization beam modes can give hints on the primeval gravitational waves. So the global plan in the field is to continue with advanced detector and to make much discoveries, maybe also unknown sources, to have a third generation detector, at least one in Europe and one in the US, to expand and to make cosmology to go in a good part of the universe to detect gravitational wave sources, and then to observe at low frequency gravitational waves with a space mission. Well, we had the eyes to see the universe. Now we have also the sense of hear the sound, the vibration. We will know better what happens in the universe. I will end with this Marcel Proust's statement that the real trip of research is not to see new landscape, but to have new eyes, because nothing will be seen as before. Thank you for your attention.
Thank you very much for this very, very interesting colloquium. And so now, questions.
What is the value of amplitude of the relic gravitational waves is expected, and is it possible to
Say again. Say again, please.
what is the value of the amplitude of relic gravitational waves is expected, and is it possible to detect them in principle?
Well, this is an interesting question because it depends on the theory you believe. There are many models of this gravitational wave emission at the beginning of the universe. The amplitude is very, very small. It's so small that you must rely on detectors better than what we have now, so a new generation, and you have to rely in detecting a coherent signal in the background noise. This is the difficulty, in the background noise. So there are two difficulties there. One is if there is the signal and if there is this thing, which is also due to the fact that to have this kind of detection, you need two detectors at a distance below the wavelength that you want to investigate. Because only if they are within, well below a wavelength distance, then there is a forcing term on both. Otherwise, if the distance is too large, respect of the range of frequency in the background that you want to detect, you have no choice. And this is not easy to do, you see, because, for example, LIGO and Virgo are too far. And even the two LIGO are too far. So you should have detector collocated, in principle. But if you collocate detectors, you have a common noise, which is the environmental noise. So this kind of source is very difficult to detect. I think they have to wait for LISA to do the kind of search. We can now put upper limits, but they are not so, let's say, exciting.
Okay. Other questions?
Just a curiosity. You mentioned that the astronomical detector will have another frequency range.
For the astronomical, for LISA.
LISA.
Yeah, this is at 10 to the minus 2, 10 to the minus 4 hertz.
The question is
low frequency, very low frequency, and so supermassive things.
Yeah, the question is why it is different. It's the dimension of the detector. What makes it different? It is easy to understand? Explain.
Yeah. Let's say that for the interferometers on the Earth have, experimentally speaking, a wall at 1 Hertz. If you put something on the Earth, you have a seismic noise and Newtonian noise, which limit you below 1 Hertz. The Newtonian noise is the noise due to the gravity fluctuation, which induced to surface wave, for instance, density fluctuation, and which are impossible to shield. You can do your best for seismic noise, but not for Newtonian noise. So this is why we want to go underground, to minimize the impact of this noise. However, you cannot go below 1 Hertz for terrestrial interferometers. This is one of the main reasons to go to the sky, because then you get rid of the terrestrial noise, and then you can go in completely another frequency range. The reason why LISA cannot detect kilohertz is that you have a transit time between the detectors, so it cannot detect fast things at that point.
Okay. Other questions?
Hi, I wanted to ask if
louder, please.
Can gravitational waves be focused via gravitational lensing, like light?
That's a very interesting question, dear colleagues. How you do reply to that?
Yes, we studied that. Yes, course, you can okay. Yes, you can lace the gravitational waves by, for instance, by even cosmological structures. That's been studied, and it's something which can be used to characterize structures in the universe.
Even the gravitational waves feels the mirror effect, however. Okay. Thank you.
Okay,
He was right.
Other questions? Sorry.
So you have been part of the first development of the technologies for detecting gravitational waves with bar detectors, right? You are part of the actual detectors for detecting.
Collaboration.
Yes. What will be the future for the Italy about gravitational waves?
For LISA?
No, I don't mean LISA. I'm talking about in general, and in particular, I would like to know more about Einstein telescope and
Yeah. Well, okay. So at that moment, we think to push sensitivity and have a long run of observation with LIGO and Virgo as much as possible. The plan is to go above 2030. So it's not tomorrow that we will stop. We are just that. Then, in the meantime, we will prepare the next generation. Next generation have now two main lines of development. One is in Europe, is to have a triangle detector with at least 2, maybe 3 detectors co-located in the same site. This will have the advantage of measuring the polarization of the wave. This is something very important because I didn't push on that. But in a binary orbit, when 2 black holes or 2 neutron stars merge, the orbit can be, respect to the point of view, this one, this one, this one, and the spin of the 2 objects can be this one, this one, this one. And this is very important to understand these things. For instance, it is expected that primordial black holes have no spin, respect to the spin formed by stellar collapse. And the position of the orbit is important to understand if there is a counterpart like gamma ray burst. In the case of the August 17 detector, source, the binary pulsar, for the binary neutron stars, they had a faint gamma ray burst respect to the proximity of the source. The source was very near. So this is why probably the orbit was not oriented well respect to the Earth, but oriented very, very badly. So this means that maybe we lost or considered far previous gamma ray bursts seen in the story. All that to say that it's important to understand the polarization and to understand this feature of the source. So the ET vision is to have a low-frequency detector and a high-frequency detector co-located in the same site underground to reduce Newtonian noise, to go to the lowest possible frequency, and to also to detect quite big black holes merger. The black holes, which, if they are large, they may merge not in the frequency band of the Earth interference, they may merge before. They will is something for LISA, but we would like to have at least So the idea of in Europe is this ET project. We have a preferred site, actually, which is in Sardinia, which is perfect from the point of view of the seismic noise and on the noise. In the meantime, in the US, they are developing another concept. It's not a triangle, not a interferometers and triangle, but one large interferometers, 40 kilometers long. ET is 10 kilometers, the side. 40 kilometers long, on ground, not underground. So simpler, if you want, if not for the length, of course. Now in Italy, it will be possible to realize something 40 kilometers, but in the US, they have space for doing that. And so we have these two concepts on which we are working. I think in a couple of years, we have to merge or to go taking into account a different view, which also may be interesting, however, because the detectors are quite different. They point more on higher frequencies, on the neutron stars. So I think both concepts are fine. Now, when they will be funded, this is a question of big science, because the cost of this object is from 1 to 3 billion euro, which is already competing with high energy physics projects. And so this depends on the science politics. And however, I think that the field has now gained a scientific credibility because of the sources we have seen, that I'm sure that the third generation will be on the agenda of the agencies in a couple of years. And in the meantime, LISA is an approved mission from ESA and NASA, so I'm quite confident.
Okay, thank you. Maybe there is the time just for a last quick question, if any. Okay, if not, let's thank Professor Coccia again for this very nice colloquium. Thank you.